Okay, I'll try to make it a bit shorter since I have less time. And it's more or less an overview about my first and latest paper that went out in November. So just to give you the idea of the paper, since I have not so much time, it's more based on the ideas more than the calculations themselves, but all the calculations are in the paper, the technical details. So I'll first come with the motivation and historical timeline that led us to work about that. Then the first scheme that was proposed was by Nicolas and Sofiane Blisdir, and then we generalized it to for 2-mode scheme, a 3-mode scheme, then an n-mode scheme, fully general, and yeah. So this is what we're gonna do. So optimal estimation of parameters encoded in the current state quadrature. So the first work was by Nicolas and Sofiane, and they saw that you could use phase conjugated states and try to measure the quadratures of two-phase conjugated states, and by a measurement setting that was more optimal than doing it on identical states. So you have two states with the same energy, two current states, same energy, just the way that you had to encode the information in these states. If they were phase conjugated, it was looking more efficient than just two identical states. In 2008, they made an experiment about that, and it confirmed their expectations. They tried to prove that enhancement, but they were not able, and so now we provided a theoretical proof, and this is yeah, mainly what is in my paper. And we also extended all that scheme to a 2-mode, more general 2-mode scheme, 3-mode, and n-mode, as we will see. So these are phase conjugated states. So you have two phase conjugated states. You can see them as a current state evolving in time, and a current state and a second current state evolving backwards in time. And so they have anticorrelated. Yeah, they have p quadratures which are opposite. So the scheme by Nicolas and Sofiane is that just to prepare phase conjugated states, then you send them into a balanced beam splitter, you apply homodynamic detection, and the goal is trying to measure the quadratures of these states with the minimum variances. And so in order to compare, we can compare them with identical current states. So this is what we are gonna do. So you assign some values for the x quadrature and p quadrature, for example, a and b, and since this one is phase conjugated with the other one, you have a minus b. And then you send them into a 50-50 beam splitter, and what is happening is that actually now they are aligning on the quadratures axis in the phase space. So what we are doing is actually kind of concentrating all the information about one parameter, which is here, and in one state, and concentrating all the information about the other parameter, which is b in the other state. And so now we can just make homodynamic detection, and we know that the variances that we have will be just 1/4 because of that square root of 2 factor that we had. So not to compare this with another scheme where you have two identical states. You start with two identical states, you send them in the same kind of beam splitter. What you have at the output is, again, you have a concentrated state, so one is now the vacuum, on the other one you have concentrated, you have a square root of 2a in the x quadrature, and a value of square root of 2b in the p quadrature. However, you need to make heterodyne detection in order to access this information, and this is adding some noise to your experiment, so your variances are only 1/2. So yeah, we have something better by using these phase conjugated states, and the goal is trying, so this was experimentally confirmed, and the goal is to try to understand why is it that, and how we can use that and generalize to other schemes. So the proof for that is based on metrology. And so in the serverless scheme, we have a set of two parameters, A and B, and a set of initial states, which are two phase conjugate states. And if you want to estimate parameters and find bounds on estimated parameters, you usually use the quantum Cramer-Rao bound in terms of the quantum Fisher information. And we have a nice formula for that if you are dealing with pure states, which we are. So we can just apply that, that we can just calculate this quantum Fisher information. And you can do it for both states. And you find that actually the quantum Fisher information is just a diagonal matrix for for alpha and alpha star. And you have a nice property for the Fisher information, which is that it is additive. So you can just add both F alpha and F alpha star, and now you have the Fisher information matrix for your system of conjugated states. And if you apply that in the quantum Cramer-Rao bound, you need to calculate the inverse of that matrix, which is easy. And you find that the variances, the optimal variances you can achieve on estimating A and B is actually 1/4. So which is met by the scheme introduced by Nicolas and Sophia. So now we extended that, and so we have a new scheme. Here you see we have another designing for encoding the parameters in our current state. And actually, we have a total energy constraint. So we are putting some energy constraint just to be able to compare it with other schemes. That will have to fulfill the same energy constraint. And now our encoding is a bit more complicated, and we just have now a T parameter, which is actually the transmittance of our beam splitter. And so we use that as initial states, and as you can see, by doing that, they are now aligned now on an ellipse. And so we use that as initial states. We send them into a beam splitter with a T transmittance. And again, at the output, what you have is two current states which are now aligned on the X and P quadrature. So you have concentrated all the A information in one state and all the information about the other parameter in the other state. And so you can again make homodyne detection, and you find an optimal variances on your estimators. So we compared the performances of this joint measurement towards an individual scheme where you are just measuring the X quadrature on the first state of the first initial state, and the P quadrature on the second initial state, without sending them into a beam splitter. And so we have that kind of graph, and what we can see, interestingly, is that the more optimal, the enhancement, the maximum enhancement is for the serverless measurement. So when you are using exactly phase conjugated states, so when your transmittance is 1/2. So you have there a factor 2. You can see we have a factor 2 enhancement for the Serre-Iblis-Deer measurement scheme. So from there, we were able also to design a free mode optimal scheme where you are encoding now 3 parameters, A, B, and C, into 3 current states in such a way that you now have like 2 parameters, T1 and T2, and then you need to send the 2 first one into a beam splitter, then make a small phase shift, and then a second beam splitter on the mode 2 and 3. And then again, you just need to make homodyne detection, and you can estimate all 3 parameters optimally. So from that, we could design an optimal scheme, and in order to design that optimal scheme, we had to put some constraints and fulfill some conditions. And the conditions is that energy condition, where we are just fixing the energy of the system in order to be able to compare different scheme. The attainability conditions. The attainability conditions is a bit more technical, but mainly it assures you that all parameters can be estimated simultaneously, so that you can always find a basis where all projectors are, where all observables are commuting. And then you have the equal precision conditions, which means that all parameters are equally important, so you want to measure them with equal precision. So there is no parameters that's more important than another that you want to estimate more precisely. And if you are fixing all these conditions, you can form a set of constraints on the what we call encoding parameters, which are this square root 2t, which are depending on these transmittances. And if you do that for an optimal scheme like n-mode scheme, you can show that these conditions are actually constraining the set of encoding parameters such that Alice just needs to encode all her parameters, one parameters in each mode, for example in the X quadrature. Then she applies a unitary beam splitter, a unitary Gaussian passive operation. She sends that to Bob. Bob applies the inverse of that unitary passive operation. And then he just needs to make homodynamic detection, and he will recover optimally the information about all the parameters. So this is the most optimal scheme that you can design. And what you can do also is use what we did, like using encoding the two first parameters into the two first current states, then the third and the fourth in the third and the fourth current states, etc. And at the end, encoding through all three parameters in the two or three last current states, depending on the number of parameters you have to encode, and then you can just apply a mix of our scheme, of our two-mode scheme or three-mode scheme, and you will optimally measure and estimate all the parameters you have encoded. So conclusions are the following. So we're able to prove the optimality of the Serre-Iblis-Dief scheme. We found a family of two-mode optimal measurement scheme, then a family of three-mode optimal measurement scheme, and finally we were able to show that how to build an optimal n-mode optimal scheme for encoding n parameters to n current states and estimating them all optimally. So this is it.
Can we go back to this slide with the fish thing?
Yeah.
Because I mean there was no time. I didn't.
Okay.
That's right. Okay. I just want to check. So you're using this. Yes. Okay. So you're using the visual information to get the accuracy, like the precision. Okay.
Yeah. Yeah.
Okay. Yeah. I just didn't have time to go.
Yeah. Actually, what we really did is that we defined a linear encoding of parameters. So we said, okay, you can encode linearly as you want the first parameter into the X quadrature of the first mode, the X quadrature of the second mode, the P quadrature of the first mode, P quadrature of the second mode, and then you can calculate all this. And it's a bit more complicated, but when you are applying all the constraints, it's reduced to that. And so you can prove that, okay, that 1/4 is really the optimal one. You can do it. Yeah.
So this is an optimal practical scheme that to send n parameters under those conditions, essentially.
Yes. Yes.
It's absolutely optimal in the sense of what could be sent to quantum states, right? There is no the quantum.
The quantum states are current states. Yeah, you are reduced to current states.
Could there be other states that are not coherent, or?
They could, but
Is this an absolute bound?
It's an absolute bound, given the. It's an absolute bound if you are using. It could be different, actually, depending on which state you are using as encoding states, you can enhance that bound. That bound will move, but for current state, this is the optimal bound. Yeah. Yeah, otherwise you can use entanglement, you can use squeeze states, and then you can enhance these bounds. This is,
Triangles just do better, but, yeah. Maybe just I can just compare them to be almost eigenstates of one of the quadratures, so send one send of that.
yes. Yes. The idea is that you have two types of, when you are measuring phases, for example, you have that SQL bound, that standard quantum limit bound, and then you have that Heisenberg bound. And we are actually reaching the SQL bound, which is, you cannot do better with current states than that, but we are reaching it, which is not usually the bound say you can reach it, but it doesn't give you a recipe to how to reach it, and we give the recipe for current states, like this is how you should do to reach the SQL bound for current states. Then you can use more exotic states like the noon states and stuff like that, and then you can go to a tighter bound, to a lower bound, which is the Heisenberg bound. But then you need noon states which are difficult to prepare, etc., etc. Yeah.
Can I ask something again?
Yeah.
It's a bit relevant, but I think I'm missing something. Because, so how do you get that F? So the F that you get is matrix here, right? So this matrix you get it through this formula that you have there.
Yeah.
This formula seems to be a number, or not? Because you have inner product, inner product, inner product.
Yeah, these are the elements of the Fisher information from matrix. Yeah, it's the elements.
Sorry, okay,
Yeah, yeah.
Yes, so that, okay, good. I can.
Okay.